Hey everyone, and welcome back to the deep dive. Today we're going to be tackling something you specifically requested. And to be honest, it's a topic that kind of had me scratching my head a bit at first.
Oh,
Yeah, we're going deep into the world of surface pressure. And, this idea that getting a surface perfectly flat
okay.
might not actually be the be-all, end-all, like
Yeah.
the holy grail we always thought it was.
Interesting.
Yeah. You sent over some research. It was titled The Pragmatic Pursuit of Pressure Uniformity, a focus on alignment over flatness. And wow,
Yeah, that's
it had some pretty wild stuff in there, talking about how getting things perfectly flat might not always be the best way to go, and that
Yep.
sometimes controlled deformation can actually be a good thing.
Yeah, and this is especially true in fields like, semiconductor manufacturing and
Yeah.
precision optics,
Right.
where
Yeah.
you need incredibly precise control over surfaces.
It really does make you rethink some assumptions, especially because I think instinctively, most of us just kind of assume that flatter is better, right? Especially when we're talking about building really precise machines or high-tech gadgets or anything like that.
It's kind of intuitive, right?
Totally. But this research seems to suggest otherwise, so help me out here. Why isn't perfect flatness all it's cracked up to be?
Well, it's kind of like chasing a mirage, you know. Even at the most microscopic level, true flatness is, well, it's kind of an illusion.
Wait, seriously? I mean, we've got these machines now that can polish surfaces to be insanely smooth, so what's going on at a level that we can't even see?
Well, even if we could somehow overcome the limitations of our tools and measurement techniques, there are these fundamental laws of physics at play here.
Okay.
Did you know that quantum mechanics actually tells us there's this inherent uncertainty in the position of atoms?
Okay, but you're gonna have to break that down for me a little.
So picture this, right? You've got this seemingly perfectly smooth surface, but when you zoom in to that atomic level, it's actually in constant flux.
Right.
The atoms themselves are never truly still.
So even if we could achieve perfect flatness, it would be like for a split second and then it'd be gone.
Exactly. It's like trying to nail down a wave.
Wow.
You just
And
can't do it. And then on top of that, you've got all these other factors at play, like temperature fluctuations, right?
uh,
Which cause materials to expand and contract. And then there's the internal stresses within the material itself, even the tiny boundaries between crystals and the material, they create these microscopic discontinuities.
so it's like this constantly shifting, almost like breathing surface.
Yeah, you can think of it that way.
No wonder it's so difficult.
Yeah.
But you mentioned something earlier that really got my attention. This idea that striving for ever flatter surfaces can actually be counterproductive.
Oh, yeah, absolutely. Think about it, right? You keep pouring more and more resources, more effort into achieving these microscopic improvements in flatness. But at a certain point, you hit these diminishing returns, right?
Yeah.
Those tiny, tiny gains, they might not even make a difference in how the surface actually functions in the real world.
Interesting.
And not to mention, it can actually make things more fragile and way more expensive to maintain.
It's like spending hours polishing a grain of sand, right?
Yeah, exactly.
You might get it perfectly round, but was it really worth all that effort?
Exactly. And a perfectly flat surface, even if we could achieve it, would be so incredibly vulnerable.
Yeah.
The slightest change in temperature or pressure could just throw everything off. It just wouldn't be practical at all.
So what's the alternative? This is where the research's like alignment paradigm shift comes in, right?
Right.
It's like throwing out the old rule book and starting fresh.
Yeah. And it's really the exciting part, right? The research suggests that instead of being fixated on this idea of perfect flatness, we should really be focusing on how surfaces align with each other.
Okay.
You can actually achieve a uniform pressure distribution, even if the surfaces themselves aren't perfectly flat.
So it's less about each individual surface being like perfectly smooth and more about how they fit together, like puzzle pieces almost.
Exactly. Think of two puzzle pieces,
Yeah.
right? They don't have to be perfectly smooth to fit together snugly. It's about the contours and how they interlock with each other.
Yeah.
And get this, sometimes controlled deformation can actually enhance that fit.
Hold on, controlled deformation? Are we talking about like intentionally bending or warping things?
In a very precise and calculated way, yeah.
Wow.
We're talking about dynamic alignment systems
Mm.
that can use sensors and actuators to constantly adjust the surfaces in real time, compensating for all those tiny imperfections we were talking about earlier.
So like a self-adjusting puzzle.
Yeah, exactly. No matter how the pieces might warp or shift over time, it always maintains that perfect fit.
So working with the material, not against it.
Precisely.
That's a pretty cool concept. But I'm having trouble like picturing how this alignment thing actually works on a practical level. What are we talking about here?
Well, the research talks about a couple of key methods. One is called kinematic coupling, which relies on some pretty clever mechanical design principles.
Kinematic coupling. Okay, I'm definitely going to need you to, like, ELI5 that one.
Sure. Imagine a three-legged stool, right?
Yeah.
You know how it never wobbles, even on an uneven floor? That's because those 3 points of contact will always find a stable balance, right?
Right.
So kinematic coupling uses that same principle to create stable and repeatable contact between surfaces, even if they're not perfectly flat.
I get it. So it's like strategically placing contact points to ensure a secure fit, regardless of any minor imperfections.
Exactly. It often involves things like self-centering mechanisms and these stress-free mounting techniques to make sure the surfaces are always, like, consistently aligned the way you need them to be.
That makes sense. But what about the other method, the one that uses real-time adjustments? That one sounds way more high-tech.
Yeah, that one's all about feedback and control.
Okay.
Think of sensors that are constantly monitoring the pressure distribution between the surfaces,
Okay.
and then using actuators, tiny motors essentially, to make these like microscopic adjustments,
Oh, wow.
keeping everything in perfect alignment, even as conditions change.
Wait, so we're talking about machines that can actually adjust themselves at a microscopic level?
Yeah.
That's pretty wild. But with all this talk about alignment, does that mean we just forget about surface preparation completely? Like, we
Yeah.
don't have to worry about smoothness at all anymore?
Well, not quite. While we're not chasing absolute flatness anymore, surface prep is still important for establishing a good baseline and ensuring consistency, right? Think of it like this. You still need a reasonably well-made puzzle piece,
Uh,
even if it's the overall fit that matters most.
so instead of trying to get the surface perfectly flat, we're focusing on meeting the specific level of smoothness that's actually required for the job.
Precisely. And it opens up some really interesting new considerations. For example, we might intentionally add texture to a surface to enhance its function, even if that makes it technically less flack.
Intentionally making a surface less smooth. Now, that's counterintuitive. Can you give me an example of that?
Sure. Imagine a surface with tiny grooves or dimples designed to, like, channel fluids or improve grip.
Okay.
Those features would technically make the surface less flat, but they could be crucial for its performance in a particular application.
Wow, we really are flipping the script on everything we thought we knew about precision and smoothness. So where is all of this already having a real-world impact? The research mentions some examples, right?
Yes, it highlights some really compelling cases where this alignment approach is already making a huge difference. For instance, in semiconductor manufacturing, dynamic alignment systems have been a game changer.
Oh, really?
They've significantly reduced defects, increased production throughput, and led to much greater consistency in the chips being produced.
Okay, so those are some pretty big wins. But what about applications where you absolutely need ultra-precise surfaces? Does alignment work in those cases too?
Absolutely. Even in a field like precision optics, where you might think perfect flatness is like the ultimate goal,
Right.
optimizing for alignment is proving to be much more effective, especially when you incorporate these dynamic systems. We're talking about lenses and mirrors that can adjust themselves in real time to maintain perfect alignment, even as temperatures change or the equipment vibrates.
So it seems like this shift from flatness to alignment is shaking things up across a bunch of different industries. But before we get ahead of ourselves, I want to bring this back to you, the listener. How could these advancements impact your own work or areas of interest?
That's a great question. It really depends on what you're working on. But if you deal with any kind of precision manufacturing, surface interactions, or systems that require uniform pressure distribution, this paradigm shift could have major implications.
So whether you're designing medical devices, building robots, or developing new materials, this is definitely something to keep on your radar.
Absolutely. And it's not just about the immediate applications.
Right.
What's really fascinating is how this concept could change the way we approach design and engineering in a more fundamental way.
Mhm.
We're moving away from this rigid pursuit of perfect flatness and embracing the possibilities of controlled deformation and dynamic adaptation.
It's like we're learning to work with nature instead of trying to force it into a box.
Exactly.
But I have a feeling we're just scratching the surface here. What's next on our deep dive into the world of alignment?
Well, next, we're going to dive into the future of alignment. We'll explore some of the crazy new technologies emerging in this space. Think AI-driven alignment systems, materials that can change their shape on their own, and even the possibility of real-time deformation compensation. Get ready for some serious mind-bending stuff.
Sounds like we're about to venture even deeper into the rabbit hole. Stay tuned because the deep dive is about to get even more interesting.
Welcome back to the deep dive. Before we jump into the future of alignment, I want to circle back to something you mentioned earlier. You're asking about how this all applies to the listener.
Oh, right.
And I think it's a really crucial question.
Yeah.
Let's say you're someone who, I don't know, works with machines or designs products or even just builds things as a hobby.
Hmm.
How might this new understanding of alignment actually change your approach?
That's a great point. It's easy to get lost in the technical stuff, but ultimately this deep dive is about providing practical insights. So for our listener out there who might be thinking, okay, this alignment stuff is cool and all, but what does it actually mean for me? What would you say to them?
I think the biggest takeaway is this shift in mindset, right?
Okay.
For so long, we've been conditioned to think that precision equals flatness.
Right.
But now we're seeing that there's a whole other dimension to consider this idea of intentional dynamic alignment, which can actually be more effective and more efficient than simply chasing a perfectly flat surface.
So it's like we're expanding our toolbox.
Exactly.
You're not throwing out the old tools completely, but we're adding these new ones that allow us to achieve precision in a totally different way.
Precisely. And that opens up all sorts of new possibilities.
Yeah.
Imagine being able to design systems that are more adaptable, more resilient, and ultimately more functional, all because you're working with those inherent imperfections of the materials rather than trying to, eliminate them.
And speaking of possibilities, I think it's time we dive into the future of alignment. We were teasing some pretty mind-blowing stuff before the break: AI, self-adjusting materials, even real-time deformation compensation. It's like we're stepping into a sci-fi movie.
It really is a glimpse into a very exciting future.
Yeah.
One area that got me particularly intrigued is the development of AI-driven alignment systems.
Okay.
Imagine systems that can learn and adapt in real time, constantly optimizing alignment based on massive amounts of data and feedback.
So we're talking about systems that can basically think for themselves, constantly tweaking and adjusting things to maintain perfect alignment, even as the environment changes around them.
Precisely. It's like having a microscopic robot constantly monitoring and adjusting things at a level we can't even perceive.
Wow.
And it's not just about software either.
Okay.
We're seeing these incredible advances in material science too.
Huh.
Researchers are developing materials that can actually adjust their own shape and properties on demand.
Hold on. Materials that can change their shape on their own? You're going to have to explain that one.
It sounds crazy, but it's becoming a reality. Think about materials that can respond to changes in, temperature, pressure, or even electrical signals by altering their shape or stiffness.
Okay, that is pretty mind-blowing.
It is.
So we're talking about surfaces that can actually morph and adapt to maintain perfect alignment, even in really extreme conditions.
Exactly. Like something out of a sci-fi movie.
Right.
And it gets even wilder. Researchers are exploring the possibility of real-time deformation compensation.
Real-time deformation, what now?
I know, right? It involves systems that can detect and counteract these tiny deformations that occur within a material as it's being used.
Can you give me a concrete example of how that might work?
Sure. Imagine a high-precision cutting tool, like the kind used in manufacturing.
Okay.
As it cuts through a material, the tool itself experiences tiny deformations, right? Due to heat and pressure.
Right.
But with real-time deformation compensation, sensors could detect those deformations, and actuators could make micro-adjustments to the tool's shape, counteracting those deformations and maintaining perfect cutting precision.
So the tool is basically correcting itself on a microscopic level to make sure it's performing perfectly.
Exactly.
That's incredible. So what are some of the other potential applications of this?
The possibilities are pretty vast, right? Think about adaptive optics for telescopes that can compensate for atmospheric distortion in real time,
Mm-hmm.
leading to incredibly sharp images of distant stars and galaxies.
Wow.
Or medical implants that can actually adapt to the changing conditions within the body, providing more effective and personalized treatments.
It sounds like we're on the verge of a whole new era of engineering and design,
I think so.
where materials and systems can adapt and respond to their environment in ways we never thought possible.
Absolutely. And what's really interesting is this research is also driving innovation in other areas, like sensor technology and control systems. To achieve this level of dynamic alignment, we need incredibly precise and responsive sensors and sophisticated algorithms to interpret the data and control the actuators.
So this pursuit of alignment isn't just changing how we think about surfaces and materials. It's pushing the boundaries of what's possible in sensing and control technology as well.
Exactly. And as these technologies continue to advance, we can expect to see even more incredible applications emerge in the, coming years. It's a really exciting time to be following these developments.
This has been an incredible journey. We've gone from debunking the myth of perfect flatness to exploring the mind-blowing possibilities of self-adjusting materials and AI-driven systems. But I think what's most important is how we bring this all back to our listener, right?
Right.
What are the key takeaways for them? How can they apply this new understanding of alignment to their own work, their own thinking, even their own lives?
That's a great point.
Yeah.
It's not just about the technical marvels. It's about that shift in perspective.
Right.
So, in our final segment, we'll be exploring some thought-provoking questions and some final insights to leave you pondering, long after this episode ends. Stay with us.
Welcome back to the deep dive. We've been on quite a journey today, haven't we?
We have.
From atoms just jiggling around to surfaces that can morph on demand, this whole concept of alignment has really changed how I think about precision and engineering.
Yeah, it's a real paradigm shift.
It is. But like we were saying before, the real power of this knowledge comes from applying it, right?
Absolutely.
So let's step back and think big picture here for a second.
Okay.
What are the key takeaways for our listeners? What can they actually do differently now based on all this?
That's the question, isn't it?
Yeah.
$1 million question.
I think for me, the biggest takeaway is we need to stop thinking just about flatness.
Yeah.
For so long, we've been obsessed with achieving this ideal state of perfect smoothness. Right.
But as we've seen, it's not always the most effective or efficient approach.
Exactly. And I think this has implications way beyond just manufacturing and engineering.
Oh, yeah.
This whole idea of alignment, of finding the perfect fit, even when the pieces themselves aren't perfect, feels like it could apply to so many other things.
Absolutely. I mean, it's like you said earlier, this isn't just about technical marvels, it's about a shift in perspective, right?
Exactly.
So let's throw this out to our listener, a thought-provoking question. All the research we looked at today mainly focused on alignment in the context of building things,
Right. Yeah.
What if we took this concept to other areas, though? Like, what if we start thinking about alignment in terms of social systems or economic models, even just personal relationships?
Now you're making me think. What would it even look like to embrace imperfection and focus on finding the best fit rather than always striving for some unattainable ideal?
Yeah.
How could that change how we approach challenges and solve problems in those areas? Those are some really great questions, and honestly, I don't have the answers, but that's the beauty of these deep dives, right?
It is.
It's not about finding all the answers. It's about sparking new questions,
Absolutely.
challenging our assumptions, and opening ourselves up to all these new possibilities.
Yeah. And who knows, maybe our listener will be the one to take these ideas and run with them.
Yeah.
Maybe they'll be the ones to discover some new application
Yeah.
for this idea of alignment that we haven't even thought of.
That's what I love about the deep dive. It's not just about, passively absorbing information. It's about actively engaging with ideas, making connections, seeing the world in a new way.
Couldn't have said it better myself.
Well, on that note, we're going to wrap up this deep dive into the fascinating world of alignment.
It has been fascinating.
Until next time, keep diving deep.